In building a capacitor, we start with acres and acres of dielectric material, high-quality polymeric materials. The problem is how to get all of this material into one capacitor can. Well, of course, we don't start with material in this form. It begins on a bobbin. And this material is then put on a winding machine. And it is wound under controlled pressure and tension into a roll which looks something like this. It's a very hard, tight roll which is then put in the can. Now, most engineers who have come in contact with capacitors think of them in terms of black boxes. What I would like to do today is go beyond the black box approach. I would like to talk about what is actually in that box, how it is constructed, what are the different changes in technology that have occurred over the last few years, and what are some of the basic concepts behind the operation of that capacitor. The capacitor is composed of two electrodes and a dielectric. It's a very simple device. The dielectric is usually made of a polymeric material, such as polypropylene, polyvinylidene fluoride, polycarbonate, or some other polymeric material. It can also be paper. The electrodes are usually aluminum, but they can also be a vapor-deposited metal, such as aluminum or zinc. When a voltage is placed on the capacitor, we see that a charge will reside on the surface of the electrodes. That charge in coulombs is expressed by the equation, the capacitance times the voltage. The capacitance is expressed in farads and the voltage in volts. Now, the capacitance can be calculated from what is known as the capacitance equation. It is equal to a dimensional constant, K, multiplied by the dielectric constant, epsilon, and the area, A. And it is divided by the thickness of the dielectric, T. The operating stress that we can impress on our dielectric material is expressed by this equation. Is equal to the voltage that we want to place on this dielectric divided by its thickness. The function of a capacitor is to store electrical energy. The energy is expressed by the equation 1/2 CV squared. This simple capacitor construction can be represented by the equivalent circuit, which is shown here. The pure capacitance is shown as a capacitor. The resistance of the dielectric is shown here in parallel with the capacitance. And any resistive losses which are in series with the capacitor, for example, electrode contact losses, are shown as a resistor in series with this parallel combination. The dissipation factor of this device is a composite of the dissipation factor of the dielectric, primarily due to the R sub D, plus the dissipation factor of the electrodes due to the series resistance. We can calculate these two terms using this equation, where we see the dissipation factor is equal to 1 over omega, which is 2 pi times the frequency, times the resistance of the dielectric multiplied by the capacitance, plus 2 pi times the frequency times the resistance of the electrode contacts multiplied by the capacitance. At low frequencies, we see that the dissipation factor of the dielectric tends to dominate. At high frequencies, the electrode contact losses dominate the dissipation factor. We will see later in discussing metallized capacitors that this high frequency dissipation factor measurement can be used as a measure of the quality of the electrode contacts. Now that we're all experts on the fundamentals of capacitors, I would like to discuss some of the main constructions that are used for high, medium, and low voltage capacitors. In the low voltage area, approximately below 500 volts, metallized polypropylene is used. Aluminum is vapor deposited on the polypropylene film. As we move to a higher voltage, the electrode changes to metallized paper. Again, polypropylene film is the dielectric of choice. As voltage is increased still further, we again see the use of polypropylene film. However, here the film has a textured surface called hazy film and embossed foil. Now let's take a close look at each of these designs, starting with the low voltage area. Historically, in this voltage region, the capacitors have always been constructed of paper dielectric and aluminum foil electrodes. They've been impregnated with a PCB, or polychlorinated biphenyl fluid. This has served us well in the time period from 1940 through 1977. For environmental reasons, the fluid was then changed to a non-PCB liquid. For example, the phthalate esters. A typical example would be dioctyl phthalate. The stress that's applied to the paper is approximately 18 volts per micron. The dissipation factor is 0.3%. In 1977, a revolutionary change took place in low voltage capacitors. Metallized polypropylene film was introduced as a dielectric. The electrodes were 300 to 500 angstroms of aluminum. The stress, as you can see, took a dramatic jump to 500 volts per micron, and the dissipation factor plummeted to 0.2%. This capacitor could either be made impregnated with a fluid like polypropylene glycol or in a dry form. What's behind this change to polypropylene film? Well, I think one obvious reason was the lowering of the dissipation factor. No longer did we have to worry about thermal runaway as we did in a paper construction. Dielectric heating was no longer a major concern. I believe the other factor was a unique feature of the polypropylene film capacitors, the clearability. This unique clearing process is shown here. On the left we see a dielectric with a defect present. This defect may be a dirt particle, a hole, or a scratch, or any other defect in the dielectric. During operation, this defect can cause a momentary breakdown. An arc can exist between the two electrodes, as shown in the middle. During this arcing, temperatures in excess of 2,000 degrees centigrade can exist in the dielectric, which vaporizes the dielectric and the aluminum electrode from around this defect site, isolating it from the rest of the electrode area. This takes place in approximately 10 microseconds and involves an almost imperceptible reduction in the capacitor voltage and charge stored on the electrodes. An electron microscope picture of a piece of film containing a clearing is shown here. In the center, we see the defect area, which is surrounded by a demetallized area. And finally, surrounding that is the aluminum electrode. This clearing, or self-healing property, allows us to reliably operate very thin polypropylene films at extremely high stresses. We can easily demonstrate the clearing process in metallized film. All we do is take a piece of metallized film, which is shown here, lay it over a conducting copper electrode. The aluminum metallization is present on the top part of the film. We contact that metallization with this contact here. We then put the safety shield on, and we apply the voltage. As we increase the voltage up to 50 volts, we see the dielectric film starting to suck down. Starts to pull tight up as we increase it even further. We're now at 100 volts. Increase it further, we're up to 500 volts. We see that there's no clearings in this metallized film. Now if I decrease the voltage, and I can apply a few defects in the film. Now I will increase the voltage, and we should see some clearing activity. Increase it to 50 volts. You can see the film start to pull down. 100 volts. Now we're at 500 volts. 600 volts. It's tough film. I'm going to have to do a better job of creating defects. Okay, let's try this again. Increase it to 50 volts, 100 volts. There's a few clearings. 500 volts. $800 volts. 1,000 volts. You see that all of the defects which I created in this film have been cleared out. The clearing process is a very important part of the operation of a metallized capacitor because it allows it to be operated at very high stresses. However, it is important that the clearing be successful. By successful, I mean that it will eliminate the metal from around the defect area without damaging the adjacent layer of film. If the amount of energy that's dumped into a clearing is very high, there is a possibility that we could damage the adjacent layer of film. This could lead to a clearing in that layer, which could then lead to a clearing in the layer that's next to it. A runaway clearing process could result, which would eventually fail a metallized capacitor. To study the clearing process, we've built model capacitors. They are essentially two sheets of metallized film sandwiched between glass plates. We apply voltage to the two metallized films, and we measure the amount of energy that takes place in a clearing. We do this with the following circuit. The model capacitor is inserted in this circuit in the position of the capacitor C sub T. To operate the circuit, we first close switch A, which charges up the 1 microfarad capacitor to a voltage V. We then open switch A and quickly close switch B. The full voltage is then instantaneously applied on the model capacitor, causing a clearing event and a current pulse in the current transformer. This pulse can be recorded on a storage oscilloscope and is shown here. We see a comparison of the current pulses arising from the clearing events for metallized film with different resistivities and different applied voltages. Integrating the area under this current trace, we can calculate the clearing energy. We see that the thinner, higher ohms per square electrodes requires much less energy to clear than the thicker 1.4 ohms per square electrodes. As we create clearings at 400, 700, and 1,000 volts, we see that it takes considerably more energy to successfully clear electrodes at the higher voltages. Running several tests of this nature, we can develop a relationship for the clearing energy as a function of the electrode thickness and the applied voltage. In the case of the electrode resistance, we see that as the electrode resistance is increased, the clearing energy quickly is reduced. This energy is inversely proportional to the square of the resistivity. In the case of the applied voltage, we see that as the voltage is increased, the clearing energy rapidly increases. According to the relationship, the clearing energy is proportional to the voltage to the 4.7 power. It is also interesting to note that as the clearing energy increases, the size of the clearing also increases, as does the amount of damage to the adjacent sheet of film. It is important to keep the clearing energy as low as possible, because there is danger that the films adjacent to the clearing arc will be damaged during the clearing process. As you can see from this graph, this can be a problem at very high voltages. Since this clearing process is very, very critical to the operation of a metallized capacitor, one would automatically assume that we should do everything that we can to lower the clearing energy. From this graph, one could conclude that this could be done by increasing the electrode resistance. Capacitors have been built with high electrode resistance materials and placed on accelerated life tests. It has been found that these capacitors have a very rapid decrease in capacitance. They do not short even under very high voltage application, but they do exhibit the drop in capacitance. The capacitors were taken apart and autopsied. In the upper part of this slide, we see a picture of the polypropylene film as it appeared before it was wound into a roll and placed on an accelerated life test. Following the life test, we discovered that there were spots present in the polypropylene film. They were clear spots. At first it appeared that the electrode has been dissolved away. However, upon scratching these clear areas, we found that a brittle material was remaining in these areas. Looking at this spot with the electron microscope, one sees that indeed there is material left in the center of this clear site. In the center here we see the aluminum oxide material. In the edges surrounding that is the aluminum metal. X-ray and electron diffraction have confirmed that this material in the center is a gamma form of aluminum oxide, an insulator. Again, we can use our model capacitors to study this electrochemical corrosion process. We sandwich two sheets of metallized film between two glass plates. We put it on voltage, and over a period of a few hours, we can see the initiation of these corrosion sites through a microscope. The growth of a particular corrosion site is shown here. We have identified one particular corrosion site as it initiated and photographed it 40 hours later. This is shown in the upper left-hand section. 12 hours later, we see that it has increased its diameter. This is shown in the upper right-hand area. 12 hours after that, it was photographed again, and again 12 hours after that. And in each of these photographs, we see that the diameter has increased in size. We can measure this diameter and obtain an idea of the growth rate of these corrosion sites. It is interesting to note that these corrosion sites are almost perfectly circular in shape, which we believe is a result of the high field effects that occur on the outer edge of this capacitor. Here we see the diameter of a corrosion site, which is plotted as a function of time that our model capacitor is on test. We find that the corrosion grows at almost a linear rate. This suggests that the corrosion products are uniformly distributed over the entire surface area of the film. We also note that the growth rate is strongly dependent on the electrode thickness, or the resistivity. Here we are plotting the growth rate as a function of the applied voltage on the model capacitor. We see that as the voltage is increased, the growth rate increases rapidly. As we would expect for an electrochemical process, the growth rate is higher at 80 degrees than it is at 23 degrees. Several studies of this nature have been performed using models in which we do everything possible to remove the sources of oxygen. Analysis have been run on the film, and we've seen that there's approximately 300 parts per million of oxygen on the surface of the film from the corona treatment. In addition, there's about 300 parts per million of water present in the film. And this is where the oxygen comes from that allows the aluminum to be converted to aluminum oxide. Also, alternate materials, which are non-corroding, have been used. Using these devices, we're able to produce capacitors that do not corrode. This has permitted us to increase the resistivity of our electrodes and also improve the clearability of these capacitors. They can now be operated at higher stresses. The effect of this new technology on the change in capacitance that we observed during life test is shown here. Life tests were run on 40 microfarad capacitors that were rated at 440 volts to demonstrate the improvement that could be obtained by using non-corrodable electrodes and by removing the various sources of oxygen. The capacitance loss is plotted here as a function of time that these capacitors were on life test. The Gem 1 designation indicates the standard processing and standard aluminum electrodes. It shows a much higher capacitance loss than those present with the Gem 3 capacitors, which have the improved processing and non-corrodable electrodes. Here we see a comparison of the effect of the high resistivity Gem 3 electrodes compared with the lower resistivity Gem 1 electrodes. The breakdown voltage is plotted as a function of the percent survival. We see that the Gem 3 electrodes provide approximately 36% higher dielectric strength than the Gem 1 electrodes. I believe this is a classic example of how understanding failure mechanisms can lead to improvements in capacitor technology. Through these improvements, we're able to increase the voltage from 300 volts up to 500 volts in a metallized construction. So why not increase the voltage even further? I think one reason is because a new mechanism becomes important. Partial discharges become a key factor in the performance of a metallized capacitor above 500 volts. During the winding process, it is very difficult to eliminate all the voids present in a capacitor roll. It is wound as hard and tight as possible, almost like a solid piece of plastic. But it is inevitable that there will be some voids present in this roll. It's further observed that during thermal cycling, that the roll will expand and the outer part of the roll will become loosened. And as it contracts, it will stay in a loosened form. Voids can develop in the outer parts of these rolls. And at high voltages, especially above 500 volts, partial discharges becomes very important. Here we plot the change in capacitance that occurs due to partial discharges as a function of time on life test. The partial discharges erode the dielectric material, which then causes a clearing. A clearing, it removes part of the metal electrode, and this causes a change in capacitance, a reduction in capacitance. Each clearing activity, each clearing event removes a very small amount of metal. But yet, when they're all added up, it leads to a very large change in capacitance, as is shown here. In the case of a dry capacitor, in which only air fills the roll, a large and rapid reduction in capacitance is observed. If one would monitor the number of clearings during this test, we would find that this capacitor is undergoing continuous and high levels of clearings. We can see that the number of clearings can be reduced and the capacitance stability improved by a high-strength gas, such as SF6 or Freon. The most effective way to quench the partial discharges and clearing activity is to fill the capacitor at the edge and in the outer turns with a high-strength liquid, such as polypropylene glycol. For this reason, we find that most low-voltage metallized capacitors are constructed with a fluid surrounding the roll. This is especially true for those operating in the upper part of the low-voltage region. It is likely, however, that as we learn more about these partial discharge mechanisms, that the dry, air-filled capacitors will be able to be used at higher voltages. We can use this clearing process to give us a measure of the quality of polypropylene film and the number of defects that are present in the film. By taking a film sample or a capacitor roll and energizing it, we create clearings. By counting the number of these clearings that take place as a function of the voltage which is impressed on that film, we can get a measure of its quality. We see that for very low voltages, less than 500 or 600 or 700 volts, there's very little clearing activity. As the voltage is increased to 1,000 volts and on up to 1,500 volts, we see a dramatic increase in the number of clearings. Thus, we conclude that the dielectric strength of the film is approximately 1,500 volts for this particular film sample. This way we can get a measure of the quality of polypropylene film. The applications that use metallized film capacitors are varied. There's motor, pump, and fan applications, lighting applications, and air conditioning applications, and many others. To test the capacitors to these applications, several tests have found to be useful. You can measure the dielectric quality, as I mentioned, by counting the number of clearings versus the voltage. The shooting contact is the contact that we make by means of a zinc spray process to the end of the roll. You'll notice that the end of this capacitor roll is coated with zinc. This is obtained in a spray process where the zinc is sprayed onto the end of the roll and makes contact with the aluminum electrode. The quality of this contact is a very critical part of the operation of the capacitor because we count on it to carry all of the current that is needed for this capacitor. One test of the quality of this contact is a high-frequency dissipation factor measurement. You will recall that the high frequency is used to emphasize the series resistance that's present in a capacitor roll. One such source of series resistance is the shooting contact area. The probability that an electrode will corrode and provide a capacitance life during its service can be obtained by the use of model capacitors, as we have shown. But ultimately, the proof that a capacitor will operate, will work, and will provide reliable service in an application is ultimately obtained by an accelerated life test on a full-size capacitor roll, where we'll test the capacitor at 80 to 100 degrees C, which is 10 to 20 degrees higher than its operating ambient temperature, and an accelerated voltage of about 25% higher than the rated voltage. It is important that this test be thermal cycled in order to simulate the application environment. There are many things which take place in this capacitor during a thermal cycle test that are not present at a room temperature or a constant temperature. The capacitor is expanding and contracting. Voids are created and removed. Therefore, it is important to run thermal cycle tests. I'd now like to take a look at the technologies, and changes of technology in the medium voltage area. Again, for many years, the paper foil construction was the old standby. It was impregnated with a PCB fluid, and it was stressed, again, at 18 volts per micron, and had a high dissipation factor. Thermal runaway was a problem in this type of a capacitor, as was dielectric puncture. The paper was fairly porous. With time, polypropylene film was introduced in 1965 into a sandwich construction with the paper. The result was a dramatic increase in the stress in that capacitor to 53 volts per micron. This is due to the high intrinsic dielectric strength of the polypropylene film. In addition, we see that the dissipation factor was reduced by a factor of 2 because of the low dissipation factor present in the polypropylene film. PCB fluids were used in this construction up until 1977, at which time non-PCB phthalate ester impregnants were used. In 1979, metallized paper and polypropylene film construction was introduced. Metallized paper allowed us to use a metallized construction and obtain the good clearability found with a metallized electrode. In addition, the rough surface on the paper allowed the full impregnation of this type of a design. The stresses were increased up to 72 volts per micron. Again, because polypropylene was the main dielectric, the dissipation factor was 0.02%. The impregnant that was used in this design was dioctyl phthalate mixed with phenylxylyl ethane. This fluid had a low enough viscosity to fully impregnate this design, and yet had acceptable chemistry to aid the clearing process. Much of the things that we've learned in metallized polypropylene capacitors do apply in this medium voltage design. As we go to higher voltages, we find that the clearings, the amount of energy in a clearing, also increases. One concern in this type of a design is the effect of thermal cycling and the presence of voids in the dielectric leading to partial discharges. In the next slide, we see the effect of partial discharges that can take place within a capacitor roll. Here is a scanning electron microscope picture of the surface of polypropylene film that has been taken from a capacitor after accelerated life testing. On the left, we see the waxy appearance of this material, which we believe to be the fluid which has been converted under partial discharge activity to a wax. On the right, we again see this waxy material with pits present in it, which are caused by repeated partial discharging. Ultimately, this may result in clearings in this area. The solution to this partial discharge problem is to use higher space factors, and constructions in which the liquid can move in and out of the roll more readily. Tight control of winding in these metallized paper and polypropylene designs is very critical in order to do this. Now I'd like to move even higher in voltage to the power capacitor area. Again, historically, paper was the primary dielectric material and foil were the electrodes. PCB impregnants were used up until 1977, at which time some non-PCB fluids were introduced. In 1965, a major change occurred in the capacitor industry. That was the introduction of polypropylene film as a dielectric material. It had a dramatic effect on the dissipation factor, reducing the capacitor dissipation factor to 0.05%. The stresses also increased to 49 volts per micron. Had a very dramatic effect on the size of that capacitor. The construction that was used was 2 sheets of polypropylene film with a sheet of paper in between them. The paper was used as a wick to pull the liquid into the capacitor roll. The fluids that were used after 1977 were either a blend of DOP, dioctyl phthalate, and trichlorobenzene, or a hydrocarbon fluid, such as phenylxylylethane or MIPB, monoisopropyl biphenyl. As time marched on, we learned how to remove the paper in this construction. And now the constructions involve 2 sheets of a textured polypropylene film. The paper was removed and the texturing on the polypropylene film is used to pull the liquid into the roll. Embossed foil is also used to aid this impregnation process. The stress is approximately the same as that has been used in what is called an inverted sandwich construction, but the dissipation factor is even lower, 0.02%. This is very important because of the emphasis on energy savings in power utility applications. The fluid that is used in this design is a very important factor. Hydrocarbon fluids are used almost extensively. PXE and MIPB are the primary fluids. Some of the critical properties of the fluids are shown here. The primary function of the liquid is to penetrate the roll, to move in between the electrode and the film to fill the entire capacitor roll. As you can see, in a roll of this size, you're asking the fluid to do a lot. You're asking it to move from the edges and completely impregnate the entire roll. To do that, the fluid must have a very low viscosity. Also, it's important that it doesn't swell the polypropylene film very much, because if it swells the film, it can close up those important spaces between the film and the foil. Another factor that involves the chemistry of the fluid, the percent aromaticity. By the aromatic content, I mean the percentage of the number of carbon atoms that participate in aromatic double bonds. So now we find that the gas absorption, that the percent aromaticity is a very important parameter because it affects the gas absorption of the fluid. Looking at some of the primary dielectric fluids which are used today, we see that first of all, the mixture of DOP, dioctyl phthalate, and trichlorobenzene has a fairly low viscosity, very, very little polypropylene swelling, and a moderate amount of percent aromaticity and gas absorption. PXE has an even lower viscosity. PXE is phenylxylylethane. it swells the film a little more and has very good gas absorption. Isopropyl biphenyl is another important fluid. It has a low viscosity, it has more polypropylene swelling, and very good percent aromaticity or gas absorption. Another fluid is diisopropyl naphthalene. Again, low viscosity, fairly high percent polypropylene swelling, and fairly good percent aromaticity. And lastly, benzylnyl caprate. Has the lowest viscosity of all, has a fairly low polypropylene swelling, and only moderate or low percent aromaticity. These are some of the primary fluids that are used. And the performance of these fluids in the capacitor is a very critical point in determining the reliability of this capacitor roll. One must be concerned that when this is taken to a very low temperature and the liquid contracts, that the liquid can move in and out of the roll. When the temperature increases and the liquid expands, it expands out of the roll. When the temperature is reduced, the liquid must be able to move in the roll. Even though the temperature is very low